Okay, so this presentation is on regression analysis and covers the material needed for homework 5 and 6. Now, regression is probably the most important concept, or the one you're going to use the most in this program and in, I would say, real life as an analyst, kind of at the predictive modeling level. We're going to talk about how to do regression in several softwares in this program. I think in this class we'll do it in RapidMiner and of course Python, because that's kind of the overlying theme for this course. And then eventually we'll also do regression in R and probably Excel as well. So we'll cover all the important softwares and how to do regression eventually. But in the live session, I believe we're going to talk about it with RapidMiner and probably Python this week. All right, so let's get started talking about regression. So regression modeling demonstrates the relationship between a single numerical target variable and one or more independent variables called predictors or features. In regression, the target variable is the one being predicted. In linear regression, the relationship between variables is represented by a straight line that best fits the data. So if you think about this visualization here, we have a scatter plot of dots represented by the square feet of a house by the price that it sells for. Then we're going to fit a line into that data, and the best fit line is what the regression algorithm is going to find. You also, if you recall from slope-intercept form, the slope of that line is what we're really interested in. So y equals mx plus b. We would see the the y-intercept somewhere over here, and the slope is kind of what we're most interested in, because when we get to interpreting regression, it's going to be that slope or that coefficient or beta number for what we can actually use to apply this in a real world setting. Simple linear regression. It is used when the focus on the analysis is limited to a single numeric dependent variable and a single independent variable. Most often, the regression line is estimated using ordinary least squares, which is a method that is the most common for very basic or simple or multiple regression. So as the name implies, this is the most basic method, but can only provide answers that are equally basic. It still has a place in analytics. So like I said, we have our basic slope-intercept form, y equals mx plus b. So, and then this is the error term. So we don't generally include that in lower level math, but the error term is something we're always trying to minimize in analytics. But you'll see this notation is much more common at higher levels of mathematical learning. So B1 is our first beta coefficient, similar to m or slope, and beta 0 is our y-intercept. So those are both values that are very important for interpretation of a regression algorithm and how we apply it to make decisions. So something to remember for the future. So here's a good definition of what the error term is. Accounts for the variability that's not explained by the linear relationship between x and y. So multiple regression determines whether two or more independent variables are good predictors of a single dependent variable. This is a very common method in analytics. The R-squared measures the amount of variance in the dependent variable predicted by the independent variable. So the dots are plotted and a line is drawn to demonstrate the best fit. A tighter model has a higher R-squared value. So what that's saying is how these dots fall or near this line. So an R squared of 1 would mean all of the dots are on the line, and an R square of 0 would basically be the completely random scattered plot with like a horizontal line. So basically the line doesn't fit the data at all. And the R squared we're trying to optimize or maximize our R squared to get as close to 1 because that tells us how good a model is. Now, in real life, it's domain specific. So in hypothetical math world, R squared of 1 is achievable, but which means all the data and our analysis fits perfect. But in many disciplines, especially in business, especially in the kind of business models that I develop, you can end up with R squareds less than 0.1, and that's all right because that's as good as they can get when you have real world data and it doesn't necessarily fit that well. That's usually when we'll start looking for other kinds of modeling situations. But anyways, R squared is very important. We'll talk about it more on the output. Um, it's usually one of the first kind of metrics I look at after I've run a regression model. Okay, so when creating a predictive regression model, determining the purpose of the analysis is a crucial step. Identifying the relationship between the dependent and independent variables is part of descriptive modeling. Explanatory modeling identifies causal inferences using theory-driven hypotheses. However, predictive regression is the most common regression model in advanced analytics. So each type of modeling uses a data set to estimate the relationship between the target variables and the predictors. And then validation data is the part of the data used to assess the model, how the model was developed from the training data. So a test data set is created to use for model validation. So let's see. That's just kind of basic terminology for homework. Okay, so the table shown here has the primary differences between descriptive and predictive modeling. So descriptive modeling is used to represent the association between independent and dependent variables in a retrospective way. Predictive modeling uses a prospective view to predict a new observation. In descriptive modeling, the focus is on interpreting the coefficients and the strength of the relationship between the dependent and independent variables. In predictive modeling, the focus is on predicting new data records. In descriptive modeling, the entire data set is used to build the model, whereas in predictive modeling, the data set is usually divided into a training and test set or validation set. Descriptive modeling uses coefficients, significance, goodness of fit, and R squared as performance measures, and predictive modeling uses the validation data set metrics and compares them against a benchmark. So when we get into actually applying regression, all those terms will come back up. The coefficients are the beta 1, beta 2, beta 3, etc., are the coefficients to each of our x variables. Significance is important because basically it's based on statistics. If we have an alpha of 0.05 and then we run a hypothesis test saying it's less than 0.05, well, linear regression is really just running multiple hypothesis tests from that. Goodness of fit is how well the model fits, but generally I just go with the R squared, and that tells me how, basically how good my model is. Now, if we run multiple regressions, not multiple regression, but multiple regressions, then we can compare the R squared of like model 1 with model 2, and then if we were going to deploy a particular model, then we'd probably want to go with the one with the higher R squared since we know the data fits better. Okay. So mean absolute error measures the absolute difference between the predicted and actual values of the model. Root mean squared error, RMSE, indicates how different the residuals are from 0. And mean absolute percentage error is the percentage absolute difference the prediction is on average from that actual target. With each of these, lower values indicate a better fit. In the world that I work in, I don't ever use MAE or MAPE. I do use RMSE, but not usually with the just multiple regression. When you get into more advanced kinds of regressions and other models, then we're going to use something called the root mean square error of approximation, and that becomes very important in something a lot more advanced than this called partial least squares regression. But for multiple regression, these metrics are, I would still use R squared if I was evaluating how well something fits or performs, or how well the model performs. All right, in this table, you see some sample values for model performance. As with any results, it is important to ask if the results make sense and if they seem reliable. Right now, you might not know what these values mean or how they compare, but in the following slides, we'll take a look to answer some of these questions. So we have our training data, the validation data, and the set testing data, and these three values. And like we said, in these contexts, you want lower values mean better values. And it would make sense that the data that we train the model on would have the lowest values because it's checking the model against the data that we designed the model on. And we would expect the testing data to be slightly higher because it's not the same data that the model was designed on. So this question down here is it possible the model is overfitted? That's an important question too because there's a lot of bias that we can introduce from different ways. I'm sure we'll talk about this more in person. But overfitting a model, basically if you used all of the training data to train a model, then that model would be overfit because it would be very well designed for the exact data it was trained on, but not on new data that you introduced to the model. Let's discuss some evaluation methods that are useful to make sure a predictive model will make appropriate predictions on new data. So there's something called the holdout validation. So that's the holdout set uses most of the data, usually 2/3. So, usually like a 70-30 split to the data to build the regression model, and the remainder is used to validate the model. There's also something else we're going to talk about as we get more into the machine learning. It's called in-fold cross-validation. It divides the data set into mutually exclusive training and validation samples, or folds, generally used 10. 9 of them are used for training, and the remaining data set is used for validation. The results are then combined and evaluated. As a result, in-fold cross-validation is less sensitive to variation in training and validation sets. So there's some metrics that are really important for when we get to comparing lots of different kinds of models, and that's the AIC and BIC. So the Akaki Information Criterion, or AIC, and the Bayesian Information Criteria, or BIC, are good measures of the quality of the model and determine the best model and the future selection approaches. For these analyses, RapidMiner is commonly used, so we'll talk more about this when we go into RapidMiner. But generally, you're trying to minimize the AIC and BIC. All right. So independent variables that are categorical must be recoded using dummy variables or dummy coding. So basically you take every possibility that a categorical variable can be. Let's say you have color as a variable and let's see. Well, I'll go on with that example. And there's 4 colors, blue, red, green, yellow. Well, you'd have to develop 4 dummy variables and make, is it blue or not? So 0 or 1. Is it red or not? 0 or 1. Yellow and green, same idea. So you'd take one categorical variable and make it into 4 dummy variables. To determine the number of dummy variables needed, use the formula k minus 1, an equation that is similar to the process shown on the slide to provide the results. Maybe we'll look more at this in class, but there's something called the dummy variable trap that we'll also talk about. So when you introduce all these dummy variables, you can create a form of bias. So generally you have to create k minus 1 variables. And what that means is if we don't really need to code blue right in that color sequence, because if there's 0 red, 0 yellow, and 0 green, then automatically that case would mean it's blue. So we really only have to code 3 of them as dummy variables. But we'll talk more about that in this class, and I think the class you take after this one. Okay, if you create a model that has too many independent variables, you may have very high accuracy of the training data set, but it is unable to predict when given new data. This is called overfitting. Similarly, when a model has too many independent variables, multicollinearity is possible, which indicates that the predictor variable are highly correlated. In this case, the size of the coefficients are incorrect, and the signs of the coefficients may be reversed. So when you go to interpret your model, you'll interpret it wrong, and that can be very dangerous. Because if you tell somebody there's a positive relationship between two variables and they go in and actually make a change to that variable in real life and then it goes down, especially if it's dealing with money, then that can be very bad for you as an analyst. Some other kind of important notes to think about is there's generally a rule of thumb when you're developing these models and sample size. So every time you add a new variable, you want to have probably around 30 samples for each. So if you have 5 independent variables that you're interested in, your minimum sample size probably should be 150. So if you're thinking about like in Excel, that'd be 150 rows of data with 5 columns. That would be kind of the bare minimum you would need to get an accurate model run. Okay. So to detect multicollinearity in numerical variables, we will run a correlation matrix and examine any correlations above 0.5. Categorical variables, we add a new dummy-coded categorical variable and examine the regression estimates with the dummy variable both included and removed. If a major change occurs, then multicollinearity is probable. So when selecting features or the independent variables that we're interested in, that's important to identify the optimal subset to explain the target variable. And that can be challenging and can be done either quantitatively or qualitatively. So the selection process can be rather repetitive. All predictors must be considered. A subset is selected. Selection criteria should be applied, and then they must be refined to improve the performance. So there's automated ways and more advanced kinds of regression. There's something called stepwise regression, and you can step down or step up. So you could start with all the variables and then drop one, and then run the regression again, drop one, run the regression again until you basically determine what is the best model. Or you can slowly add variables and see how it changes the regression. But in either of those cases, you may run into something called omitted variable bias. But like I said, that's another kind of bias we'll talk about in a future class. So quantitative approaches to feature selection include backward elimination, forward selection, and stepwise selection. So that's kind of what I was just talking about. So backward elimination starts with a regression model that includes all predictors, and at each step, a variable is removed, and the model is run again to reevaluate the fit. With forward selection, initially a separate regression model is created for each predictor, and then the predictor with the best score is included, and the remaining variables are combined until no further improvement is seen. Stepwise selection adds a variable at each step, but also removes the variables that no longer meet the threshold. So this process ends when the remaining predictors satisfy the threshold and remain in the model. Okay, so this ends the presentation on regression analysis. The material covered in this presentation will help you complete homework 5 and 6. Stop.